Hello, so in this video we're going to start off with a nice little trick which we can use for standard Brownian motion, and then we're going to get into something called geometric Brownian motion. So here's a little trick. So basically it's best to kind of see it on a number line. So this is time, okay, this is time, and say if we have three time periods. So we have the time period at t equals 0. We then have the time period, let's say S, and we have the time period at t. Okay, so these are independent time periods, and obviously we're going to have Brownian motion associated with each of these time periods. So the Brownian motion, or the value of the Brownian motion at t equals 0 is going to be called b0, and this is standard Brownian motion. Remember, so at b0. The Brownian motion should be 0, or times 0, b0 should be equal to 0. Okay, so this is now then bs, and this is now bt. Okay, and we can come up with this kind of identity. So we can basically come up with an identity for b of t. Okay, because b of t is going to be this time period plus this time period. Okay, so bt, okay, is going to be equal to this time period here, which is this time period here plus this time period here. So these two time periods added together. So what is this time period here? What's this time period here? Well, it's going to be bs minus b0, yeah, bs minus b0, then plus this time period here. So what's this time period here? It's going to be bt minus bs. Okay, well, what's b0? What's b0? Yeah, b0 for standard Brownian motion is 0. We always start at 0 for standard Brownian motion, okay? So therefore this is 0. So this is another identity we can have. It can have bs minus 0, so just bs, plus bt minus bs, okay? And this is a nice little identity. It's useful, okay, because what it's basically saying is that 1 equals 1, okay? So it's kind of like, it's a bit obvious, but it's a useful identity that we can actually use to solve, say, for example, something like this. So say, for example, if we wanted to find the covariance, remember that the covariance is, if you like, just a measure of the variance between two time points, two Brownian motions, for example, in this case. So BT and BS. So the covariance of BT and BS just basically means, well, a measure of how much BT varies from BS, say, for example. Okay, well, we can break this down. We can break this down using this identity, because we've got BT now. BT, let's use this identity. BT is equal to BS. So this covariance of BT, which is BS plus BT minus BS. All right, comma BS. All right, so we end up with this. This is a linear process. You know, covariance is a linear process, which means that basically we can break it up into the covariance of BS and BS and BT minus BS and BS. So basically, we take this element from the first, if you like, the first pair. So this is one element here. This is two element here. So we take this first term and pair it with this second term, and this second term and pair it with this second element. Sorry, this first term of this first element and pair it with the second element, okay, and the second term of this first element and pair it with the second element. So let me show you what it means. So covariance of BS and BS, all right, plus, use this plus in here, plus the covariance of this second element, this BT minus BS and the BS, yeah, so we end up with that. All right. Now, what does this mean? Okay. What is the covariance of BS and BS? Well, it's basically saying, well, how much does BS vary from BS? It's just going to vary by the using the standard definition of the axioms. It's just going to be S. Yeah, it's just going to be S. The covariance, the variance of BS is just going to be S. Yeah, we showed that in sort of the last video. The variance of BS. This is effectively just the variance of BS, because we're saying, well, the covariance is how much two variables change. Well, we've not got two variables anymore. We've just got one variable. We've just got BS. Okay, BS. So therefore, what is the variance of BS? Well, the variance of BS is just going to be S. Okay, and then what's the covariance of this? So how much does this vary? Okay, so BT minus BS to BS, how much does this vary? Well, they're independent variables. So therefore, there's no correlation or connection between these two variables. There's no correlation or connection between them. So in other words, this is 0. This second one's 0, because there's no correlation and connection between them. So basically, we can use this kind of identity to deduce that the covariance of two time points in Brownian motion is just going to be equal to the time value at the first Brownian motion. So in other words, if we draw it on the graph, okay, the covariance between Let's get rid of all these arrows. Okay, the covariance between this point, BT, and BS is just going to be the time value at this first time period, which is S. Okay, so we can use that. Okay, so now let's look at some sort of some properties which we can use. So, so apart from all the properties that we've looked at before, we can also have these kind of nice properties, and I think I've alluded to these before. So basically, we've got the Brownian motion. Brownian motion returns infinitely many times to any value, and all these properties are based around the fact that that Brownian motion is a fractal. So remember what a fractal is. Basically, as we zoom in on a section of the graph, okay, it doesn't smooth out; it remains kind of jagged. So it's infinitely jagged, if you like. That's all a fraction is basically saying. So what we're basically saying is that we return infinitely many times to any value, because obviously we can zoom in on any section of the graph an infinite number of times, and it will still be jagged. We can zoom in an infinite number of times on any section of the graph, and it will still be jagged. So therefore, we've got an infinite path. So basically, there's several values. It's basically all of the properties that I'm about to show you are based on this fact that we've got kind of like a fractal going on. So it returns infinitely many times to any value. Well, look, because these paths are infinite in length, because you can keep zooming in and they keep going to be jagged, so you can zoom in an infinite number of times and you're still going to have, a path length. So basically the path length has to be infinite, okay? Then therefore it must return infinitely many times to any value. Yeah, because we've got an infinite path length, because it's a fractal. Okay, so we can choose any value. So say 5 is going to return infinitely many times to 5. If we choose 0, it's going to return infinitely many times to 0. If we choose 2,436, it's going to return that many times, an infinite number of times, 2,346 or whatever I said. Okay. The next property is that the paths are differentiable. Don't know why I'm writing in capitals. Differentiable nowhere. Okay, so in other words, we can't differentiate Brownian motion. I sort of alluded to this at the end of last video. We can't differentiate Brownian motion because if you remember, the whole theory behind differentiation is that you have a curve, okay, and you can zoom in on that curve, enough times, it basically becomes a straight line, and so therefore we can differentiate or find the gradient. That's what differentiation is related to, find the gradient of a curve just by considering a tiny section of the curve, because in that tiny section it's going to be a straight line, and we can find the gradient of a straight line quite easily. Okay, but of course with this now we've got a fractal going on, so we can zoom in an infinite number of times, and it's still going to be this jagged motion. So therefore we can't differentiate a jagged motion. Okay, so it's differentiable nowhere, and that's quite actually a nasty property. And we have to actually use something which you have to use differentiation, which is associated with like probabilities, and that's known as stochastic differentiation. And we're going to look at that shortly. Okay, not in this video, but coming up. We've also got the property, these are kind of little bit more properties, little interesting properties. If you have a path, so you've got this path, and say if we choose 2 points in this path, let's say we choose that point, and let's say we choose that point. Well, because we've got an infinite, because we zoom in on this time, we keep zooming in, and we've still got an infinite, we can zoom in an infinite number of times, and we've still got this jagged motion, going on, then therefore, there'll be an infinite length between any 2 points in the path. So there are the length between 2 points on this Brownian motion path, if you like, is infinite. Yeah. So in other words, we have infinite length, and that's purely because it's a bit like a bit of string. Okay, you lay this bit of string out. Well, you have to have an infinite length of string, effectively. So you can pick any 2 points in the path, and the points, the length between those 2 points has got to be infinite, because you can keep zooming in an infinite number of times, and it's still going to be jagged motion. Okay, so that's kind of some interesting properties around Brownian motion. Let's look at this thing called standard Brownian motion. In actual fact, I'm going to do it in another video. I've changed my mind.